This video will demonstrate how to utilize Mech-MSR to measure and inspect the height of connector pins, ensuring that workpieces meet quality standards. The measurement target is the distance from the pin tip to the reference plane, which, in this case, is the surface of the PCB board. Before formal measurement deployment, make sure to complete the preliminary data acquisition tasks. Next, move on to data processing. Here, the acquired surface data undergoes pre-processing steps, including alignment, filtering, rough locating, and secondary filtering. The alignment step aims to eliminate workpiece position deviations and ensure precise alignment. The 2D model editor helps to extract features and generate a matching model. This quickly corrects the workpiece position, guaranteeing consistency in subsequent processes. Following this, apply filtering to the aligned surface data to extract pin data, and perform initial noise reduction for smooth surface data. Then, to ensure precise positioning of each pin in subsequent measurements, perform blob analysis on the initially filtered data, to roughly locate the surface data of pin tips. Finally, conduct another round of filtering on the pin tip surface data obtained. This step removes the highest and lowest data points, effectively reducing data fluctuations and thereby enhancing the stability and accuracy of the results. With an understanding of the workflow, we can now start configuring the measurement project to achieve the desired results. Open Mech-MSR. From the solution library, find and download the connector pin height inspection solution. First, use the 3D laser profiler step to acquire images of the pins. Connect to the laser profiler. Select the previously saved parameter group from Mech-I Viewer. After completion, run this step to acquire data. Next, proceed to data processing. In the alignment step, create a matching model for image alignment. Open the 2D model editor to obtain the workpiece image. Adjusting the depth range clearly highlights the edges of the workpiece, ensuring accurate matching. Then, draw an ROI covering image feature points to quickly create the model. If necessary, we can also set the center point to locate the matching area. The angle and scale parameters define the search range as well. Adjust them accordingly to improve matching speed. After configuration, generate the model and save it. Upon selecting the generated model, the effect of model matching can be viewed in the visualization interface. As can be seen, the current model is now aligned with the workpiece's feature points. This step outputs the aligned surface data, which underpins subsequent measurement. Following this is the filtering stage. The filter surface points by normal step aids in extracting smooth pin surface data. Select the feature region, to cover the pin area to be measured. Then adjust the maximum polar angle and noise removal level. This filters out tilted noise points and irregular scatter points, yielding optimal pin data. Next, perform coarse positioning on the initially filtered data. In this process, the blob analysis step is used to detect all pin tips from the surface data. Set a suitable height threshold and apply a threshold filter. We can adjust these based on the blob's intensity Z values in the image. This allows for the preliminary screening of pin tip surface areas. Use the area filter to retain only the blobs that meet the area criteria. Subsequently, specify the rule for ordering the output blobs, facilitating precise measurement of each pin. Finally, to obtain accurate pin tip surface data, use the process surface by filter step to perform secondary filtering on the rough position data. In the advanced filters, use the percentile filter. Set high and low thresholds to remove extremes in the pin tip surface data. This ensures data stability and precise pin positioning. After completing the above configuration, start the measurement phase. It mainly involves 3 steps: obtain the pin tip center points, fit the reference plane, and measure the pin height. Then, proceed with the specific operations. To this end, use the locate feature point of surface step. Set the feature point type to average to obtain each pin tip center point position. After this, fit the reference plane with the measure surface flatness step. Select feature regions on the PCB board surface to obtain planar data. Then, to remove noise points within this region, enable the local percentile filter. Finally, fit a global plane based on the filtered data, which is the output of this step. Next is to measure the pin height using the measure dimensions by features step. Taking the previous 2 steps' outputs as the measurement basis, it calculates each pin's height by measuring the distance from their center points to the reference plane. Additionally, set the distance range to determine whether each pin's quality is acceptable based on its height. At this point, the configuration of the measurement project is complete. Click the final step to view pin height measurement and inspection results in the visualization window. Ultimately, set quality judgment rules to enable Mech-MSR to automatically perform inspection. The inspection target here is the height of each pin, which involves multiple items. Therefore, a comprehensive judgment rule is adopted. Only when all pins are qualified will the entire project's judgment result be okay. Follow the instructions. Open the Output Management window. Select the Quality Judgment tab. Choose the corresponding project and judgment type. Select the measurement items to be included for judgment as needed. When finished, run the project. The overall quality judgment result of the project will be displayed in the upper left corner. Now it's time to start test runs, establish communication, and conduct integration testing before full-scale production. The following video will further demonstrate these processes. For more details on pin height measurement and inspection cases, please refer to our documentation.